and thank you for the invitation. It's a pleasure to be in Paris. I don't come nearly as often as I should. OK, so I'll start by giving a little reminder of what some of these words in the title mean. And in particular, I'll start with some of the dimension theory that will come up. So the first thing is asymptotic dimension. So X is going to be a metric space. And now the definition that was introduced by Gromov is that the asymptotic dimension of X is less than or equal than some integer n if and only if for every r greater than 0, and here you think of r as being big, so this is a large-scale notion, there exists a cover of X by uniformly bounded sets with r multiplicity less than or equal than n plus 1. What I mean by r multiplicity is that if you take any metric ball of radius r, that ball intersects at most n plus 1 of the sets in the cover. OK. So you can think of some fairly easy examples. For instance, the plane has asymptotic dimension less than or equal to 2 by the standard brick cover that you use to show that the usual topological dimension has dimension less than or equal to 2, except that now the bricks are going to be big. So in other words, you would use a cover like this. So it's the same picture, but imagine that the bricks have size much bigger than this number r. OK, so here's the brick cover. OK, and so on. So if I take my ball of radius r, the best I can do is intersect 3 of these. And that means that the dimension is less than or equal to 2. OK, another notion of dimension, this time it's a small-scale notion, was introduced by Buyalo. And this is called capacity dimension. So X, again, is a metric space. We will say that the capacity dimension of X is less than or equal to n, if and only if, for every sufficiently small epsilon. And now epsilon is small, as I said. Oh, I didn't get this right. So there exists a constant c greater than 1. So that for all sufficiently small epsilon, there exists a cover of X by sets of diameter less than or equal to epsilon and of epsilon over c multiplicity less than or equal to n plus 1. So I c is something like 100. So the sets have to have size about epsilon. But if I take a ball of size epsilon over 100, that's allowed to intersect at most n plus 1 of these sets. So one way that so you can kind of associate some pictures in your mind with this notion is, how would you, if I give you, say, a funny metric in the plane, how would you try to estimate the capacity dimension? Well, you could try to find some kind of a cell structure in the plane. So I don't know. Here's a cell structure, and then the cell structure is going to have its usual handle decomposition that's associated to it. This doesn't have to be any kind of a regular cell structure. Just anything will do. And then once you have one of these things, you can try taking little neighborhoods of. You start by taking neighborhoods of vertices. Those are sort of 0 handles. And then you take neighborhoods of edges, but you delete the neighborhoods of you delete the 0 handles that you already constructed. So maybe think of all these cells as having roughly size epsilon, and then these balls that I start with are going to have size maybe epsilon over 10, and then I'm going to take epsilon over 100 neighborhood of every edge and delete the 0 handles. So my next collection of sets in the cover is going to be some kind of a picture like this. These are the 1 handles. and so on. And then when you get to the top dimensional cell, you just delete from the top dimensional cell all the handles that are already constructed. And now with luck, if the cell structure has a reasonable geometry, this is going to be a cover like as required in the Buyalo definition. So what are the requirements here? So you want to know. So you want all cells, well, of dimension greater than 0. You can't do this for the vertices, but you want all cells to have roughly size epsilon. It shouldn't be that the ratio of size is big, right? That should be bounded. So all cells are of size roughly epsilon. And you also want to, there are also some bad pictures that you don't want to see. For instance, you don't want to see a picture like this. Okay, so here's maybe a quadrilateral, but in the metric, in the underlying metric, maybe it looks like this. So the cell has size epsilon, maybe, but the distance between these two opposite faces is maybe much less than epsilon. In other words, the ratio between the distance between these two faces and epsilon maybe goes to 0 in my sequence of covers. Then this is no good, right? I cannot use these covers to estimate the capacity dimension. Okay, now the theorem that relates these two notions is the theorem of Buyalo, which says that if you have a hyperbolic graph, so let's say x is a delta hyperbolic space or graph space. For us, it's just going to be a graph, which is delta hyperbolic. Then the asymptotic dimension of x is less than or equal than the capacity dimension of its boundary plus 1, where the metric on the boundary is the visual metric. So boundary of x, this is just the Gromov boundary of this hyperbolic space, is equipped with the visual metric. And you can look at its capacity dimension, and then there's this inequality. This theorem is not too difficult. You can prove it with some work from the definitions. But there's a deeper theorem, which we won't use, that's due to Buyalo and Lebedeva, that says that equality actually holds if x is the Cayley of a hyperbolic group. Okay, but we will only need this inequality. Okay, so this is this ends the first part that's about dimension theory. Okay, now let's talk about the curve complex, or the curve graph. We'll really only use the one skeleton. So the higher dimensional simplices will be irrelevant. So sigma is going to be a hyperbolic surface, and for simplicity, I will take it to be closed. But in principle, you can have punctures. So sigma is a hyperbolic surface and closed. And then the curve graph, so this is the curve graph or curve complex. So the vertices are just geodesics, simple closed geodesics on the surface. So simple closed geodesics in sigma, and you put an edge if the geodesics are disjoint, or you put a simplex if you want, if the corresponding geodesics are pairwise disjoint. Okay, so a simplex corresponds to disjointness. Okay, now it's hard to draw these things, but in the low genus case, namely of the puncture torus, which I don't want to think about punctures, but if you want a picture to associate with this, it's the Ferri graph. The Ferri graph is the simplest example of a curve complex, and it's associated to the puncture torus. Although there you have to modify the definition slightly, but it looks like this. It's a theorem that you can draw it without lifting the chalk. Let's see. Anyway, what you're going to notice is that it is locally infinite. It is a locally infinite graph. This definition was given by Henri in the 70s, and then it was used later by Henri, who also proved a lot of topological properties of this in his work on on homological stability. And then a big step forward in understanding of this complex came with the work of Mazur and Minsky, who showed that this complex, this curve complex, is hyperbolic. Okay, so Mazur and Minsky showed that C of sigma is delta hyperbolic. And in fact, now there are very simple proofs of this fact. Maybe the simplest one is due to Hensel, Pshititsky, and Webb. Just a few pages. Okay. Oops, that's the wrong one. Okay. Okay, so the theorem that I want to talk about is joint work with Ken Bromberg. So this is all with Bromberg. And the theorem is that the asymptotic dimension of the curve complex, so this is now in genus G, so sigma has genus G, say, is less than or equal than 4G minus 5. Okay, which is curious because this is exactly the virtual cohomological dimension of the mapping class group. Okay, now there's some history here. So first of all, Bell and Fujiwara showed that the asymptotic dimension of a curve complex is finite. They used there is this argument that goes back to Gromov, showing that every hyperbolic group has finite asymptotic dimension. So they used Gromov's argument, which doesn't really work here because the complex is locally finite. So Gromov shows that the asymptotic dimension of a hyperbolic group is bounded by something like the number of elements in the ball of radius delta, if the Cayley graph is delta hyperbolic. That's in principle some large number, and it's really from Buyalo-Lebedeva that we can compute the asymptotic dimension exactly. But for the curve complex, this bound is infinite because the delta ball in the curve complex will contain infinitely many points. So that argument doesn't really work. But what Bell and Fujiwara use is a notion of a tight geodesic. So these are some special geodesics in the curve complex are called tight. And that notion also goes back to Mazur and Minsky. And Bowditch proved appropriate finiteness properties for this notion of a tight geodesic. So they can use Gromov's argument and replace geodesic wherever it occurs in Gromov's argument by this notion of tight geodesics. However, they couldn't write a single number that's a bound on the asymptotic dimension of a curve complex, and that's because this the Bowditch theorem was not effective. It was a finiteness theorem that was proved by assuming the infinite and then taking limits and getting a contradiction. So there was no specific bound that Bowditch had in his theorem. Now later, within the last year, Richard Webb gave an effective proof of Bowditch's theorem, and that led to a specific number that one can put here from the Bell-Fujiwara proof. Richard Webb at Warwick. Richard Webb. I decided not to. I'm going to say a lot of names, so I decided not to write any of them. Okay, so here's a student at Warwick. Yeah, so this led to a specific number that one can put here, but it turned out that the number is exponential in the genus. Okay, now the real motivation for this work is not so much to find a smaller number, although you have to admit that 4G minus 5 is somehow. I mean, it's certainly curious why this number shows up. But the secret agenda is that this fact was a key ingredient in the proof that Bromberg, Fujiwara, and I had for that the mapping class group has finite asymptotic dimension. And we'd like to prove the same sort of theorem for out Fn. But we don't know that the complexes that are analogous to the curve complex have finite asymptotic dimension. The notion of tight geodesics is missing. So the real motivation for this work was just to find another proof of this fact that has maybe more chance of being generalized to the out FN world. Okay, yes?
The constant, the asymptotic dimension is not like equal to 5 or something.
Oh, you mean does it get bigger and bigger? Yes, it gets bigger and bigger. It depends on the genus, yes. Okay, so let me say a little more. So what we're going to show, so in fact, if you want, this is the real theorem that we prove is that the capacity dimension of the boundary of C is C of sigma is less than or equal than 4G minus 6. And this is actually a theorem of, so Gabay computed or gave these estimates for the topological dimension of the boundary. He was building on the work of Hensel and Pshititsky. And he gave this bound for the topological dimension. So it's implicit in his work that, he's going to construct cell structures like this. What we have to worry about is showing that these bad pictures don't occur. So we have to worry about the shape of the cells. Okay. So now the next thing is I want to talk about how to construct these the covers, or at least sets. Yes.
Sorry, quick question. Does all of this work in the puncture case too? And do you get VCD again?
It's not. I don't know if it's VCD. It does work in the punctured case, but I don't know if it's exactly VCD. I didn't check. Actually, in genus 0, Gabay computed the dimension exactly. So in that case, we know the genus 0 with any number of punctures you want, we have the exact number. But when the genus is positive, then there is a gap between the upper bound and the lower bound. And the size of the gap is roughly the genus. Okay, so so now I want to talk about how to construct sets that will give these covers. So these sort of cell structures. So for that, I have to recall some notions from surface theory. The first one is the so-called PML. Okay, so this is a standard object that's associated to a surface. It was introduced by Thurston, and the PML stands for projectivized measured laminations. You should think of it, if you haven't seen this object before, you should think of it as some kind of a completion of the set of simple closed curves on the surface, or simple closed geodesics on the surface. If you can imagine taking limits of longer and longer geodesics, and the limiting object is one of these things. Okay, so this is homeomorphic to the sphere of dimension 6G minus 7, and Thurston used this space to compactify Teichmüller space, which is homeomorphic to a Euclidean space of one dimension higher. Okay, so the first thing we need to understand is how to think about the boundary of the curve complex, and that was understood by Erika Claret some 15 years ago. So the work of Claret identifies the boundary of the curve complex. I guess I will write her name too. So she identified the boundary of the curve complex with what I want to think of as a subquotient space of PML. So you first take a subset of PML and you pass to a quotient space. And it's if you want something more precise, then I would say it's F PML divided by some equivalence relation. So these are filling projectivized measured laminations. In other words, these are measured laminations who support fills, in the sense that the complementary components are all homeomorphic to open disks. Okay, so that's one ingredient. Another ingredient, and perhaps the main ingredient, is the notion of train tracks. Okay, so let me say something about train tracks. So what is a train track? That's another thing that was introduced by Thurston. Okay, so Train tracks. So what is a train track? Well, it's a graph embedded in a hyperbolic surface, and it's modeled on, so it's say sigma. So it's a graph inside sigma, and it's modeled on, all our graphs are going to be trivalent, and it's modeled on this. So this is meant to represent a smooth path. So this is a smooth path, and this is a smooth path, and of course this is not a smooth path. Okay, so again, for a specific example, it's easiest to draw it on a puncture torus. So here is the puncture torus, and then here's an example of a train track. You draw maybe a simple closed curve like this, and then you go like this. Okay. So here's an example of a sigma. We will also usually require that every complementary component is an n-gon where n is greater than or equal to 2. So I want sigma minus little sigma minus this graph to be a union of n-gons when n is greater than or equal to 3. In other words, I don't want to see a round disk in the complement. That's not allowed, or a monogon or a bigon. Those are not allowed, and you're not allowed to have a genus also in the complement. So these are the filling train tracks. And for experts, we always assume that these train tracks are recurrent and transversely recurrent. Okay. So there was a lot of work done on the theory of train tracks after Thurston. There's Penner. Penner has a book with Herrer about train tracks, and then there was work by Mazur and Minsky, and then later by Hammenstadt, and we're going to use all this, all their results in this. Okay, so one notion that's important is the notion of carrying. This is somehow why the train tracks were introduced in the first place. So what does it mean for a curve? Say alpha is a curve, or we think maybe a geodesic in sigma is carried by your train track sigma. If you can homotope it, if you can homotope alpha into sigma so that it becomes a smooth path in sigma. So in other words, you're not allowed to make this kind of a turn. That's not smooth. When you get to a vertex, you have to go in a smooth way through it. So this just means that alpha is homotopic to a smooth path in sigma. And then to a train track, I can associate a few objects. We'll need maybe 3 objects or so. So I can first of all I can associate S of sigma. This is a certain subset of the curve complex of sigma, and this is just a set of curves carried by sigma, by little sigma. So a set of curves carried by sigma. It is some very nice usually unbounded, well, in this, generally, an unbounded subset of the curve complex. It's not the whole curve complex. For example, it's easy to come up with curves that are not carried. For instance, the longitude, the curve that you would draw on top of this picture would not be carried because you would be forced to make illegal turns here. Another thing I can associate to sigma is P of sigma, and this is a subset of PML. This is the closure of, if you think of PML as the closure of all curves, then P of sigma is the closure of curves carried by sigma. So these are the laminations carried by sigma. And this set has a nice cell structure. It is a convex cell, appropriately interpreted. It is a convex cell. If you have a curve carried by a train track, you can count how many times it crosses each edge here. And you're going to end up with a collection of numbers called weights. And these weights will satisfy switch equations. So if you here's a little local picture. If you have weight A, weight B, and weight C, then you see that these numbers satisfy the switch equation, namely C is equal to A plus B. And also A, B, and C are non-negative. And equations like this with inequalities that they have to be non-negative define a certain cone. And then the projectivization of the cone is this convex cell. Okay, so that's P of sigma. It's a very nice cell that sits in the boundary, in the sphere in PML. Okay, now the result that relates these two comes out of the Maser-Minsky theory. So I mean, using their theory, it's easy to show that first of all, S of sigma is quasi-convex. So it's a certain subset of this hyperbolic graph. So it's quasi-convex, and not only that, but it is coarsely a convex hull. A convex hull of what? I have to give you a subset of the boundary. It's a convex hull of a certain subset of the boundary. Well, how do you go to the boundary if you have P of sigma? P of sigma sits inside PML. Now you know, the boundary is really a subquotient. So you first intersect with where the quotient map is defined, and then you push it by the quotient map, and that's it. Okay, so this of P infinity sigma, which is P of sigma intersect F PML, and then modded out by the equivalence relation. Okay, so in the obvious way, the convex hull, so this thing is at infinity of the curve complex. So maybe the rough picture is like this. Here's the curve complex. Maybe I'll complete it over here, and here's my S of sigma, like that. And then this thing at infinity is that's P infinity of sigma, and it's convex hull. If you draw the geodesics connecting points, pairs of points in P infinity of sigma, you'll get coarsely up to bounded neighborhood. You will get S of sigma. Okay. And then there's one more notion that we will need, and that is the notion of a vertex cycle. So every train track carries a curve that crosses every branch at most twice. So those are kind of short curves carried by the train track. So let's see if I can manage this. Is this 1 or 2? I can never remember. I think this is 2, right? Yes. Okay. Yeah, so there is a notion of a vertex cycle. So this is the set of curves in S of sigma. So these are curves carried by sigma that cross every edge at most twice. And such curves always exist. So this is a non-empty set. It is uniformly bounded in the curve complex. So this set acts as a kind of a fat base point. So this is part of the structure here. There's a fat, so this S of sigma comes with a canonical base point, with coarse base point. Okay, there's one more thing. There's always one more thing. There's a notion of splitting. So if you have a train track and you find a branch that looks like, or edge that looks like this, so here's a piece of our train track. There is an edge, and on both ends of the edge, it looks like this. In other words, it's the special direction. It's the one that's not parallel to any other direction out of the vertex. And this is true on both ends. Well, then what I can do is I can split it. I can split it in 2 different ways. I can do this. So let's see. Yeah, like this, or I can do it the other way. I sort of pull them apart, and then I draw a diagonal in 2 different ways. So if this is sigma, then the splitting gives you sigma 1 and sigma 2, and then it turns out that what happens on the level of the P of sigma is that you just cut it by a hyperplane. So P of sigma gets cut. So here's P of sigma, and then you're going to cut it by a hyperplane into P. So over here we'll have P of sigma 1, and on the other side it's P of sigma 2. So P of sigma 2 is this half of the, so. Okay. Okay, so now we're ready to describe the cover. So you're going to give me a small epsilon, and I have to build a cover. Okay, so this is the procedure. Okay, the procedure starts with a certain cell structure on PML that was defined by Penner. Okay, so Penner defined a cell structure on PML where every cell has the form P of sigma for some sigma. This is actually a slight cheat because here, when the dimension of this cell is too low, then this sigma, the strain track sigma is not going to be filling. So I'm stretching the definition here a little bit. But anyway, this is certainly, you can imagine this picture. So there's a sphere, and then it's cellulated by cells of this type. Okay. Now epsilon is going to be much smaller than the visual size of the Penner cell. So remember that we're putting the visual metric on the boundary. Each one of these cells has a certain visual size. I'm going to require that epsilon is much smaller than the visual size of the cells in Penner's cell structure. And then I'm going to start cutting. Okay, so keep splitting each Penner cell, each top-dimensional Penner cell, until the visual size is less than epsilon. What's that?
Why is it possible?
What do you mean, why is it possible? I'm giving you a procedure. If it's not less than epsilon, split it again. If it's not less than epsilon, split it again.
Maybe there are no edges like that.
Oh, there are always edges like that. That's part of the transverse recurrence. So this is, yeah. So there are some details that I'm not telling you, but this is always possible.
It might not be able to get the intersection of all of these guys is you start off with equation, you want to go near the equation. So it's not easy, but
yes,
then you might get a whole.
You get the whole simplex, exactly. So this is the trouble when you have experts in the audience. No, exactly, but that whole simplex gets crushed to a point. So the visual size of that simplex is 0 because it's a point in the boundary of the curve complex. Okay. Okay. So basically the procedure. I mean, so what you're supposed to be thinking about is something like this. Here's your cell, and now you cut it in half. Now maybe this cell has size less than epsilon. Then you stop. You're not going to subdivide this cell again. You live with it, whatever it is. But maybe this cell has size bigger than epsilon, so you split it again. And maybe again one of the cells is good, but the other one is not. So this just goes on and on. In fact, notice that some cells will have to be subdivided infinitely often. It will never end for some cells because there are certainly curves. There are short curves somewhere. There is a short curve somewhere, and that short curve is going to cause the visual size of that cell. If the curve is short, then the visual size of the set or sort of the shadow that it casts on the boundary is going to be big. And so that cell, wherever that curve is, let's say it's here, however you slice it, one half will always contain this curve, and that half, the visual size will never decrease. The visual size of that cell will be always bigger than epsilon. So you'll just have to go on forever. Okay, so this is an infinite procedure. But you only keep, you keep the cells that stabilize, that reach the size less than epsilon. So the collection, we work with the collection of cells whose size stabilizes at less than epsilon. So once it's less than epsilon, you don't subdivide it again. Other cells get subdivided infinitely many times. You don't do anything with those. So just look at those cells that stabilize. That collection of cells covers FPML. So this covers, it doesn't cover all of PML. It doesn't cover these short curves, for example. But it covers all the filling laminations. All of FPML. Okay, and of course, each cell has the right size. So this is a good beginning. We have a cover kind of a cell structure, although it's kind of infinite, but it's locally finite. It's a locally finite cell structure, and all cells have size less than epsilon. But now we have to worry about those bad pictures. This is basically where the work kind of starts. Okay, so to control, maybe a little remark here, to control the visual size. So the visual size, so let's say this is the curve complex. And then I have my S of sigma here. And this comes with a base point. The whole space has a base point, namely, take the vertex cycles of the initial Penner cells. That's a natural base point to work with. Okay, so it turns out that the visual size, visual diameter, visual size of S of sigma, of the boundary of S of sigma. So this is really P infinity of sigma. The visual size, so remember S of sigma is a convex hull of P infinity of sigma. The visual size of this set is roughly A to minus the distance from the base point, the global base point, and the base point for S of sigma. So this is the vertex cycles of S of sigma. Where A is some constant bigger than 1 that you have to choose to define the visual metric. Okay, so up to multiplicative error, this is what the visual size is. In other words, when you demand that the diameter of these cells is roughly epsilon, that's like demanding that the distance between these points is roughly some fixed number, up to an additive error. Okay, so let me say in the remaining few minutes what the difficulties are and what we do to resolve this. Okay, so the first difficulty is that faces. So we can show easily from this fact that faces of these cells also have visual size roughly epsilon. Why? A face of a cell like this is really given by a sub-train track. If I have a train track defining the cell P of sigma, and I take a face. The face corresponds to saying that my curves don't pass through a particular branch. So this is going to be like saying that I'm passing to a certain sub-train track. Well, any vertex cycle in the sub-train track is also a vertex cycle in the train track. So that means that passing to a subtrack doesn't change the distance between the base point and the base point of the set S of sigma very much. In other words, faces of my cells have roughly the same visual size as the whole cell. So I don't have these pictures. I don't have to worry about getting pictures like this, where I have some kind of a big cell, and then there's a tiny face. Okay, so that doesn't happen. Okay, so that doesn't. So this is good. It doesn't happen. The bad news is that intersections of these top-dimensional cells may not be faces. You could have something like this. Let's see. Maybe I should bring the board down. Okay. In other words, you can see that when you start subdividing. Whoops, this is dangerous. When you start subdividing, you know, it's not the intersection of two cells is not necessarily a face. It's just some kind of a subset of a face. So in other words, pictures like this might occur. Okay. Okay. So even though I know that faces have size roughly epsilon, I still have to worry about this intersection having size less than epsilon. And this is where we use a slight generalization of the work of Hammenstadt. So I won't go into the details, but this is what rules out this sort of possibility. In fact, we show that if this is, say, sigma 1 and this is sigma 2, then the intersection P of sigma 1 intersect P of sigma 2 has the form P of some other sigma. So this intersection already has this form. It does, this is not clear a priori. It might be that this is just some kind of a cell, and maybe it's a union of cells of this type, but how do you know that it's one of these cells on the nose? Okay, so that's one fact, and then also the size is correct. Okay, so this as I said comes out of the work of Hammerstedt. And now the last issue is the one that's the most difficult for us. So the last issue is how do you rule out the following possibility? So you have a cell, and you have two faces of the cell, and everything is of size roughly epsilon, but these cells come very close to scale much less than epsilon. We have to rule that out. Or maybe even something like this. I don't know. I should draw this. Like that. So here, this is a triangle, combinatorially a triangle. But how do I know that the two of the faces don't come close to a very small size? That's, of course, allowed near the vertex, but it's not allowed sort of in the middle here. OK, so I need to rule that out. And I'm going to state the lemma that does that, and that's maybe the heart of the proof. So I won't have much time to say anything about the proof. I will say maybe one sentence. But I will state the lemma. And it's a train track lemma. It's about train track. So you have a train track in the surface called sigma, and then you have two extensions of this train track. In other words, two train tracks obtained by adding from the previous train track by adding branches. Okay, so this is the lemma. So you have so sigma, so tau 1 and tau 2 are two extensions. Two extensions of a train track sigma, right? So you imagine starting with the train track sigma and then adding some branches, some edges to that train track to get these larger train tracks. We'll also assume here that the edges of tau 1 and tau 2 don't intersect transversely. So they don't. In other words, the union tau 1 union tau 2 is a train track. Although it turns out we need slightly more general statement. Okay, then for every c greater than equal to 0, there exists a c prime greater than equal to 0. So that if ai is a curve carried by tau I. Okay, so you have a curve a1 carried by tau 1, and you have another curve a2 carried by tau 2. And you assume that they are close by. So the distance in the curve complex between a1 and a2 is less than or equal to c. Okay? So this is what you should imagine when you see this picture. I mean, why does this picture arise? Well, because there are curves that are very close that give rise to this picture. And then the conclusion is, then there exists a curve b that's carried by sigma. So that the distance between ai and b is less than or equal than c prime. Okay, so basically this says that if you see this picture, here's a1, here's a2, and they're kind of close to each other. Well, the only way that this can happen is that both of these curves are actually close to. So here's, think of this as being given by sigma. This vertex is given by sigma, and these edges are given by tau 1 and tau 2. So I'm giving you two curves that are close to each other, and the conclusion is, they're close to the vertex. And then that's OK. Because then these will be swallowed by the little zero handle that you're going to put over here. The one sentence I want to say about the proof is that the logic is Zilli-Salas shortening argument. You assume C prime doesn't exist, so you have a sequence of worse and worse examples. You take limits. Limits are some kinds of laminations. These laminations tell you how to modify these train tracks to get another triple tau 1, tau 2 sigma, where the statement also fails. And you keep doing this until you get back to there are only finitely many triples like this up to the action of the mapping class group. So eventually you'll get to the triple that you've seen before, but you'll have smaller counterexamples. than before. That before you thought you were working with smallest possible counterexamples, and then you discover smaller ones, and that's what proved this lemma. Okay, so I will stop here. Thank you very much.
Thank you very much. Are there any questions, comments? Your last chance. Yeah. Okay.
It seems like there's a lot of parts of this that don't have obvious generalizations around it then either.
That's true. So yes, at least now we have a different set of problems to think about. That's right. Yes, that's exactly right.
More questions?
What does not work for our system?
What is what?
Which points do not work for our system?
Well, the strain track theory. I mean, that's so basically we know that the boundary of outer space, which should be the analog of the PML, is finite dimensional. But for example, the argument that it's finite dimensional is very indirect, and this is a very explicit argument because you construct these charts that are obvious. They're cells. They're obviously finite dimensional. And so this is maybe the first place. This is step 0. I mean, what's the analog of these sets? You need some explicit charts in the boundary of outer space.
In reality definition, there is also this constant C. It's not clear how you get this constant because this C prime actually depends on this in your lemma. C in your lemma actually maybe not linearly depend.
No, so this is so this is additive. So these are constants in the curve complex. Additive error in the curve complex is multiplicative error in the boundary. And so here it's right. So here it's you're moving from C to C prime, but the visual distance moves by some by whatever. I guess it's under this board. It's a to the minus something. It's some fixed constant that depends on C and C prime.
Okay. No more questions. Then we thank the speaker again.